Hello everyone, do you hear me?
Yes, we can hear you.
Okay, thanks. So let us start with the last lecture of this course. Right. Fine. Okay, so wait 1 second. Yeah, so today we are talking about sampling methods. This is the last topic. And this is important because I mean, the motivation for this is very high, right? So, for example, you have a motivation which is to approximate. These are like tools to approximate integrals. Like imagine an integral of a function of x, depending on some parameter, times the probability of that parameter, given, for example, some data. So these sort of integrals are actually omnipresent in Bayesian inference. Right, so it is a typical thing that one needs to do. And this is because, well, maybe we haven't discussed this in detail, but this is because once you get, in the Bayesian approach, once you get the posterior distribution of your parameters, you may want to make a new prediction. And the way to do this new prediction for a new given input here, let's say, you would, the way to go here is to marginalize over all possible parameters, theta, as opposed to the frequentist approach, where you actually replace this theta by the maximum likelihood estimate and just give a prediction. Here, instead, you just marginalize over theta, thanks to having access to the posterior distribution or an approximation to it. So these methods we are discussing today will allow you to do this, but not only. I mean, you have numerical integration in general. And in particular, this applies to function optimization. Like I want to minimize a function with respect to some parameters, right? Which is actually important. This is also important in the frequentist approach. And I mean, beyond that, of course, all of this is not only in physics, but in many sciences, right? Like in biology, is very useful, engineering, whatever, okay? You name it. So it is a very important thing a very important tool to have in order to solve many of the problems appearing in these sciences. Here we are just talking about this problem, I mean, about this application of approximating integrals like this. Okay, fine. So the problem in consideration then, I mean, let me just rewrite that expression. The problem in general is to compute the expectation value of a function, right? This is a function of many parameters in general, weighted by the probability of those parameters. So this is interpreted as expectation under this distribution. Sometimes in the literature, you also see this written like this. Expectation on the distribution of distribution P of the variables. And in general, the idea in general is to approximate. So you approximate this integral by a sum. I mean, this is approximately equal to the sum, or an average, sorry, of the function evaluated in arguments where these arguments are actually samples from its distribution, right? So the idea would be take sample from it, from this, and once you get a number of L samples from this, very large number typically, then you go and for each of the samples you evaluate this function, and then you take the average of it, and that is and this is the way to approximate it. Okay. Of course, I mean, this, why is that? I mean, why this works? I mean, in general, you know that, I mean, this follows because simply and something that we have seen before, you know, that the limit where n tends to infinity of 1 over n, I mean, the limit of the sample mean is actually giving you the expected value of the variable, right? So we have talked about this before, and there is no need to insist on it, but this is a true statement here, right? Okay, what is the problem with all this? I mean, this seems like a very simple procedure. So the problem here is that in practice, it's very difficult to get independent samples. Or let me put it, truly independent samples. So the procedures in general, the way to get all these sets of samples here, ZL, the procedures that we are talking about in general, they tend to have some correlation between these samples, like they will in general depend on the others, and this is actually a problem because then it would imply that in practice you need a pretty large number of samples, right? So if this average here, if this approximation here would be like, I don't know, imagine that it would be quite accurate for, I don't know, tens of samples or maybe 100 samples, since these samples are not truly independent, you typically need of the order of hundreds of thousands of samples, or even 1 million samples or whatever. Okay. So this is important here. This is independent samples. And that is all the algorithms that try to do sampling in one way or the other, they try to solve this problem somehow. Okay, so I will concentrate in one of them in particular, but I will talk briefly about two simpler strategies. So I will talk about some basic sampling algorithms. And the first one is called rejection sampling. So in rejection sampling, you have the task is to sample from a distribution. And this distribution is typically of the following form. So you have some distribution here normalized by normalization factor. And why I say this typically of this form, because this is the structure of the posterior, right? So the posterior distribution that would enter in this expectation value that I was talking about at the beginning is like the numerator of the Bayes theorem and the denominator of the Bayes theorem. And typically, this distribution is difficult because this guy denominator is intractable. However, it is typically happening that this numerator is something that you can work with. So having in mind this frequent case of a distribution of this form, the idea here is the following. So in the rejection sampling, you have a distribution Q, which is called a proposal distribution. And then how does it look like? So let me draw like a cartoon here. So imagine that you have the true distribution is I don't know, something like this. So that would be the true distribution P tilde. And then the idea is to have the proposal distribution such that when you multiply by a constant, so for example, let me just write this distribution here, this is equal to some constant K times my proposal distribution. Okay, so so I need a constant and this constant K is such that K times this proposal distribution is always larger or equal than the distribution we wanted to sample. Okay. For all Z. So that's why it is like covering the distribution. And then the algorithm is simple. The idea is to sample a number, let me call this number Z0 from my proposal distribution. So if I do this, let me put this number like here, for example. Imagine that I have sampled Z0 and it is going here. I mean, this is Z here, something like that. So I have sampled Q. I get Z0, and this is easy because Q is a proposal distribution which is tractable, okay? And then, so I have as a second step, I sample a number, and let me call this number U0 from the uniform distribution in the range 0 K Q of Z0, K of times Q of Z0. So I am sampling this U0 like in this range here. Do you see this? I don't know. No. Okay. Right. So then the conclusion of that, or the final step of this procedure is if U0 is larger than the original distribution evaluated at Z0, then the sample is rejected. So in practice, what it means is that I am rejecting this area here. All this area here is being rejected. No, by following this step number 3, I would reject everything which is above the true, I mean, the desired distribution. And that is a way to sample from, I mean, that is a way to get samples from P of Z. Okay, so this is the algorithm. There are drawbacks of this. First of all, in practice, it's very difficult to get a good, to come up with a good proposal distribution. Okay. And this in terms of rejection rate. Of course, imagine that my proposal distribution is really flat because I want to be on top of, I want to have like an envelope, no? That I ensure to be on top of that. Or I multiply this by K, which is large enough. But imagine if K is large enough, imagine that then I have a K times Q is up here, of course, the rejection area is much larger, right? So in general, it is very difficult to have a low rejection rate. Okay. And also in high dimensions, imagine that now I am not talking about one parameter, but many parameters. This rejection rate is also very high. Okay. And it is very high because the volume grows exponentially, right? So imagine that I now have like 2 dimensions here. So the volume that you reject will increase exponentially with the dimensions, right? Okay, so but that's it about, I mean, I don't want to spend a lot of time on this. I will just discuss another very popular sampling if there is no questions on that. Okay. So importance sampling is another popular sampling procedure. And here, actually the idea is, so the idea is not to get samples from P of Z, but to estimate the expectation value in directly. But estimating that expectation value directly by doing the following. So first of all, same ingredient, similar ingredient, which is a proposal distribution. Q of Z. in general multivariate. So the idea is to rewrite this expectation that we have here as f of z, and then I multiply and divide by q, like this. And then I can approximate this integral. I approximate it by sampling from Q and evaluating this factor here, right? So this is approximated by 1 over L, sum from 1 to L, capital L, of this fraction here times the function that we want to average. And here set samples from Q. And these here are called in the literature the importance weights. And in the algorithm, actually all samples are retained. There is no rejection. There is no rejection here. So what is happening in any case is the following. What is happening is that if Q of Z is not good enough, then typically you will have many weights. Many weights are going to be close to 0. And this is why, and why is this? It is because imagine that, I don't know, imagine that P is something like, is typically, okay, multimodal, very complicated, etc. So you may have like a lot of mass, probability mass, like concentrated, like, I don't know, imagine this is in one region, but you are trying to approximate this thing by another distribution. So these weights are going to be, if Q is not chosen correctly, are typically there are just a few weights where you have more or less all the contribution, and the rest of weights are going to be very small. And this is going to give you a bad, just a bad approximation, let's say, in the end. And in general, same drawbacks than for the previous strategy, rejection sampling. Okay. So so that's why that's why one of the I mean, I will present to you now with the other method, which is the one that will dedicate the rest of the lecture, which is Markov chain Monte Carlo.
Can I ask you something?
Yeah.
So if we have a function which has like a peak somewhere, then is it this important sampling a better way to sample instead of the original probability? Because
Say it again. If you have a sample which is quite big, sorry, a distribution P, no?
Yes.
Which is quite big, then what was the
Yes.
question?
Then it might happen, I think, that this P of Z, if we know that, and we can sample from that, maybe the most values do not lie in that range of the peak. So if we just sample from P, then we won't get the correct expectation value of F.
Yeah, but you don't know where the peak is.
The peak of F?
The peak of P.
No, I mean if F has a peak.
Okay, let me try to draw in order to understand. So you are thinking about F of Z being some function with the peak like this.
Yes.
Okay, then.
Or a more narrow, let's say.
Or more narrow, okay.
Yes, then can it happen that P of Z could have could not cover the peak region? Yes.
Okay.
So if we can sample from P of Z, then we won't get the correct expectation value of F, I think. Yes. But we can solve this problem by using the Q, I guess. Or no?
No, the thing is that I think I understand the question, and probably this is going to be discussed a little bit later. But in any case, as far as I understand, I'm not like a big expert on this, but as far as I understand, the idea of rejection and importance sampling is to focus on P regardless of F.
Okay. Mm-hmm.
Right. So and this is logical, because imagine they don't want to. I mean they want to focus on P in order to create a method that hopefully applies to several options for F.
Mm-hmm.
And that's why there is no reference at all on F at this stage with these methods. Okay, it is completely true that in general what you are interested in, it is in a situation where you have both factors in the integrand are large.
Yes, right. Mm.
Because otherwise it's going to be highly inefficient. That is completely true. Let me elaborate more on this like in some minutes, because I will come back to this problem. But you are absolutely right. So if you have find a situation like this, then you might not sample from the correct distribution. But the thing is that with these methods, they will tend to sample correctly from this. And then at some point they will, if I draw Q, like, I don't know, imagine that proposal distribution is very fortunate and it is similar to it. By these methods, I won't get something covering F, because these methods are designed to sample as efficiently as possible from this distribution. So if F it happens to be away, I mean yeah, it's not a probability mass, but I mean most of the F values happens to be away from the probability mass of P. This will not be covered by Q, because Q is designed to focus on P only.
Okay, I see. Thanks.
No, but I mean, you're right. I mean, this is that would be the ideal, but I think it is very, very difficult to come up with an algorithm that works for every F and P. And I don't even think that this is something which is standard solved. I mean, probably there is someone with proposals, but standard procedures, I don't Yeah, I'm not aware of it. Okay, so let me, in any case, I will in a second, I will comment again on that. So the motivation for microchain Monte Carlo is that it scales well with the dimensions. So scales well with the dimensionality, dimension of the parameter space. So again, here the idea is to have a proposal distribution. So there is no way around it so far. So you have a proposal distribution, and then this proposal distribution is a bit different now because it is a proposal distribution which actually depends on some other value that you have obtained before. Okay, so let me just put it like this. I have a proposal distribution for a step tau plus 1, which is a function of a proposal of the sample of the previous sample. So with this, you can form a sequence. So you have set 1, set 2, in general, okay? Set tau. And then this is going to be a Markov chain. This is going to be a Markov chain because it will satisfy the Markov property that Q of set tau plus 1 only depends on the previous and not on tau minus 1, tau minus 2, etc. There is no dependence on that. It is only dependence on on the previous step. And this is the definition of a first order Markov process, let's say. Okay. So let me talk a bit about desired properties of Markov chain. For Markov chain. Well, the property that you want actually is that it should converge to the desired distribution, of course. Otherwise, we are not doing business here. So this is our goal here. So in order to achieve this, then you need to have some properties. So the Markov chain Monte Carlo should reach a stationary distribution. Okay, and then what is this stationary distribution? So imagine I have the following. So imagine that I have a transition probability. Let me call it T, transition probability of set tau going to set tau plus 1. Okay, I will remove, let me remove for notation just the vectors. So those are vectors in general. So this is just going to be just another name for the probability of set tau plus 1 given set tau. Okay. I'm talking about the true probability. of z tau plus 1 given z tau, which I don't know a priori. But then how do I compute? Let me compute first what is the marginal probability. So let me compute the marginal probability of z tau plus 1 is just an integral over z tau of this. And actually this will depend on tau. This transition probability in general will depend on tau. So this is transition between z tau and z tau plus 1, q of z tau. Okay, the dz I already included it. So once you do this, you just imagine that you can do a histogram. So you do a histogram of z tau plus 1. And then this histogram here, you get a resulting distribution, right? So this resulting distribution, you compare it with the distribution you got from the previous sample, and then you compare. So if for all tau the resulting distribution is equal, then we say that this distribution is invariant, right? Under this Markov chain, of course. Or in other words, the Markov chain has attained the equilibrium distribution. Okay. There is another property here, which is that a Markov chain where imagine that now all the transition probabilities are equal. For all z, sorry, for all tau, then this is said to be homogeneous. So now if these conditions are met, I mean A and B, then it has been demonstrated, and I am not getting more deeper into that, that for tau going to infinity, the required that the proposal distribution, the proposal distribution Q tends to the required distribution. And if this is the case, then a Markov chain with this property is said to be ergodic. It is ergodic when it tends to the required distribution, to the true distribution, let's say. And actually, there is a shortcut for having this property. And the shortcut is that a sufficient condition, and this is just sufficient, for ensuring this, I mean, for ensuring that the required distribution, this P of Z, is invariant, is to choose this transition probabilities. How was it? Z tau plus 1 to satisfy something which is called detail balance. And detail balance is nothing but P of Z, T of Z, I will just switch a prime here, is equal to the other P of Z. Sorry, I am. I think I have made a. Yeah. So the probability of going from Z to Z prime times the probability of Z, it is equal to the other thing. The probability of going from Z prime to Z times the probability of Z prime. And then the Markov chain with this is said to be reversible. Okay. Okay, so why is it reversible? It is just because I mean, when you can do it. So you the way to show it this is more or less simple. So if you start integrating or having a marginalization over Z prime, then if I apply this detail balance, then I will get, if replace Z by Z prime, so I reverse I interchange the arguments. And then Q of Z goes out of the integral, but the integral of the transition probability is just 1. So it is Q of Z. So I have obtained the starting distribution, let's say, right? So in this case, it is a reversible. So then let us continue. So with this, it is important now to have a way to implement this in practice. So one way of implementing this is with the Metropolis-Hastings algorithms. Okay, so then assume in general, again, may assume some texture for your distribution, which is given by this P tilde and a normalization of that. And I want to, P should be a stationary distribution. And then you impose detail balance. Okay. And then this is a shift, and I will demonstrate this in a second. by the Metropolis-Hastings algorithm in the following way. So you imagine you have a proposal distribution now of a new set given set tau, and I sample set tau from this. So this proposal distribution is such that the transition probability from set tau to set star is equal to this proposal distribution times the probability of accepting the new sample. The probability of accepting the new sample, let me denote it by this. This is the probability of accepting the new sample set star, where this probability is given by the following. This is the minimum between 1 and T of Z star given. This is in the denominator, P of Z tau. And in the numerator, sorry, it is the inverse. Z tau given Z star times P of Z star. Okay. So this condition enforces the tail balance. And I will demonstrate this in a second. But the, I don't know if something happened. No, okay. I thought that you were not hearing me. Okay. So before demonstrating this, then in practice, what you do is to draw a number U0 from uniform distribution in the range 0, 1. So you draw a random number between 0 and 1. And then if this number is smaller than the probability of accepting this new sample, then you do accept it. Otherwise, you reject it. Okay, so this is the way to go. So now let me demonstrate. I mean, because it is not obvious, it seems like a magical, recipe for implementing the tail balance, but actually it's not. I mean, so let me demonstrate. So let me prove this here, which is very simple. So I want to compute. What is the transition. I want to compute the tail balance, right? So let me say it the following way. I will try to go to this denominator, multiply to the left and to the right by this denominator, okay? So if I do this, then I get set of Q of Z star given Z tau times P of Z tau times A Z tau and going to Z star. This is given by the minimum. So this is given by the minimum between what? Between the same thing, Q of Z star given Z tau. So I am multiplying 1 by the same thing times P of Z tau between this minimum and the other factor, this factor. So this is Q of Z tau given Z star times the probability of Z star. And then what I do is to actually take out of this minimization, I take the other factor instead. So I will factorize this by Z tau given Z star, P of Z star times 1, but I mean actually the one is this one, and then I have instead here in the numerator I have Z star given Z tau, Z tau divided by the thing I got outside. But this is exactly the other transition, right? So this is exactly the other transition, the inverse transition, I wanted to say. So this is exactly A of what? Of Z star going to Z tau. So I have started from this and I have got this. But this is, I mean, you know that this times this is a transition probability. It's this T that I wanted to, that I introduced before. So that implies that T of Z tau going to Z prime times P of Z tau is equal to the transition from, sorry, this prime is a tau, not a prime, a star, sorry. Times the transition is equal to the inverse transition. So from Z star to Z tau given by the probability of Z star. And this is actually the tail balance. Okay, so this is a proof that this condition here, the way you compute the transition probabilities in the Metropolis-Hastings algorithm, is implementing you the tail balance, and then you have the good properties that you should have. Okay. So, as usual, this proposal distribution Q of Z tau plus 1 given Z tau has a very large impact on the approximation, on the goodness of the approximation. A very common proposal, distribution is actually the Gaussian. I mean, that you may have expected. And actually, the choice of the variance is a key aspect. So why is a key aspect? Because if two small variance, then the acceptance rate is high, but convergence is really slow. Convergence is like very slow. If on the contrary is too large, then the acceptance rate will be very small. And you don't want this either. So imagine that you're trying to have a, that would be the desired distribution. Then typically you may have a proposal distribution. So if this is so if this is sigma max and this is sigma min, I mean, roughly speaking, like a rule of thumb or whatever, that what turns out, it's not a rule of thumb, it's what turns out, roughly speaking, is that the optimal sigma would be approximately equal to the minimum sigma of the desired distribution. Okay. Another thing is that this Metropolis-Hastings, this suffers from random walk. From random walk behavior. And this means that essentially it wastes a lot of time, like wandering, right? It may go in this direction. I mean, if a point is here, you are actually exploring all the possible directions. So it is a waste of resources in a way. So I mean, it would be desirable to have some guidance of where to move next, right? And actually, this is what hybrid Monte Carlo. Hybrid Monte Carlo on Monte Carlo, or in this is in physics communities called hybrid Monte Carlo, particularly in the lattice QCD, which is actually the community developing this from the first time, I think. But it is also called Halmilton Monte Carlo. And this is a jargon mostly used in the statistics community or machine learning community. So this is like the state of the art of Markov chain Monte Carlo, and I plan to spend the rest of the second hour discussing on it. So if there is no more question, I can propose a 10-minute break. Any question? Okay, so do you hear me, by the way? Because probably I'm just talking to the wall.
Yes.
Yes, we can hear you.
Okay,
Well,
good. Thanks. So let us meet at okay. Let us meet at 10 past. Okay, 8 minutes.
good. Thank you.
Thanks. So hello, I'm back. Can we continue?
Can I ask you a question? Sorry.
Yes.
Sorry, I got confused with my previous question with the peak. So if the function that we want to find its expectation value doesn't have behaves normally without peaks, then we don't have this problem, right? Okay, but only if it is weird, let's say.
Only if it is away from the probability mass of the.
Yes, but if it is away and it doesn't have a large peak, then is it affected the expectation value so much?
The function itself doesn't it?
Sorry?
You're talking about the function.
Yes. If it is away, but it doesn't have a large peak.
No, I mean, if it is a constant, then you don't care.
Okay.
Then
if it's a normal distribution?
If it is a normal distribution with large variance, then yeah, I don't know. It depends. For me, this is hard to do. It is hard to say like a priori a statement without like looking at the function. I really probably depends on the function.
Okay.
Yeah. In any case, so this is this is something that leads me to the question of, so what is the relevant region? So
I think
again,
you are not sharing the.
Sorry?
You are not sharing the
Oh,
screen.
thanks. Yeah. Thanks a lot. Yeah. So yeah, what I was saying is that this is what you're asking is just the question that I wanted to discuss now, which is what is the relevant region? So let me just rewrite here the problem that we have. P of Z. And this is what we were discussing before. So ideally, when the product is large, this product is the largest. Okay. However, the strategies I am aware of, and the strategies in particular of the also the state of the art of sampling methods, which are this is arguably the case here, the hybrid Monte Carlo. It is again focusing on P. I mean, like expecting that it will be applicable to many functions. To many choices of F. So even if this is a smarter, what I wanted to say, even if this is a smarter way to sample, because it is guided by these motivations we were discussing, it is again a strategy that doesn't depend on F in a way. So let us focus on, but discuss a little bit more on. So let us focus on P of Z. Let me just draw it. Imagine you have something like that. So what would be the relevant region of now talking about P? what would be the relevant region of P? Should it be the region around the mode? So imagine that I wanted just to focus on the mode, and that's it. What do you think? Imagine that we design a strategy that is only focusing, capturing the mode of P. Only on the mode of P. So, well, it is not a good strategy because you may lose large probability mass coming from large tails. Right? So if you do this here, and then you only focus here inside, then you may have this problem. But then you may say, okay, I won't focus on the mode, I will focus on the tail. Should I focus? What happens if I only focus on the tail? Then focusing only on the tails, this is obviously bad, right? Because you're missing the region of high probability mass, which is the mode and the surroundings. So actually the idea is to focus instead on an intermediate region. So the idea of this HMC, this hybrid Monte Carlo, is to focus instead on the intermediate region. And this is called, I think in the literature, this is called the typical set. Okay. So let me try to draw something now. Let me choose this color. So imagine that you have a typical set of, okay, let me choose something larger. Imagine you have a typical set of this form. I don't know. Here, then the mode is inside here, right? And outside the typical set, you have the tails everywhere. No, this is tail everywhere. And this is the typical set. Fine. So the idea is to build a Markov-Chain Monte Carlo algorithm which explores efficiently. So imagine you are in a point here which actually has some guidance, like going here, not like in Metropolis-Hastings, like it can go everywhere, and you may lose you have this random walk behavior. But the idea is to design an algorithm to have guidance. And guidance in order to explore the typical set as efficiently as possible, okay? So this is going to be what Hamilton Monte Carlo is implementing. So,
but I have a question.
Yeah.
So here you're assuming that P of X is highly peaked. Because, for example, when you do, I don't know, Bayesian inference and you want to estimate the likelihood, this P of X is the prior, which is usually chosen to be very flat and so on. So
Or in Bayesian inference, the idea is to estimate the posterior, no?
yes, but if you want to do this integral, wouldn't P of x be the prior
No.
and f of x the likelihood? Or maybe I'm understanding it wrong.
No.
If you want to compute the evidence,
No, the problem we are discussing here is okay. Let me put another page here. So the problem we are discussing here is different. It is an integral where this is the posterior distribution, and this is an observable function. So let me put an example. So imagine you have a function, and this function is a function of the input and some parameters. This is a function that actually is a function that generates generative function of your data. Okay, let's say you have some data and then you want to find what is the generative function of that. So the way to go in Bayesian inference is to build first or estimate first the posterior distribution, and then try to estimate what are the predictions based on this posterior distribution. So I will use a likelihood. Let me put the likelihood, the likelihood of a point of a point yi, given of course given some point input and some parameters here. So this is going to be, for example, a Gaussian, where this generative function here, let me just change notation. This is a generative function, is giving you the mean, okay, with some standard deviation, whatever. So I have some data. I wanted to describe this data by this generative function. And the way to propose a statistical model is to say, okay, I am proposing a likelihood function, which can be a Gaussian or can be another thing, where I use this function as the mean. So this is the likelihood of a point yi. And then I use the likelihood of all the data times the prior of all my thetas, and then I build my posterior. Then the final step in Bayesian inference is to make a prediction, which is a prediction on new input. Let me put it X star. Okay. Do you follow me, by the way, or no?
yes.
Okay. Then the prediction on a new point will have a likelihood. So I want to write the likelihood of a new output given this new input and given all the data I have seen before. Let me say just training data in the context of I don't know, machine learning jargon, let's say. And this is equal to the integral that we are discussing in this lecture. So this is equal to the integral of the likelihood of this new point given the new input, given some theta times the posterior that I am estimating somehow. And this is called, in the literature, the predictive distribution. So, sorry, getting the predictive distribution is what everyone in the Bayesian community machine learning is doing in the statistics community. They are doing because they want to get a prediction at the end of the day. Okay, there are many problems in astrophysics where the final step is just this one, because you are interested just in the physical parameters and having posterior intervals of the physical parameters. But in general, in statistics, what you want to do at the end of the day is to make a prediction, and the way to make a prediction is to have is to build this predictive distribution like this. And this is exactly the integral type of integral I'm talking about. Okay, and
okay, I understand. My background is astrophysics and so on, so I was thinking of the other problem.
Okay, I understand. Yes. Yeah, with respect to astrophysics in general, this is like going a step beyond and using your posterior in order to make a prediction on a new point. Yes. And then, I mean, this is equivalent to say, okay, I want to get the expected value of a function of the new input. And this expected value is given by the integral over this function weighted by the probability, by the posterior probability. Okay. So this is the sort of thing we are trying to discuss. And in that sense, I am, while discussing this in this lecture, I always have in mind the fact that the thing that you're trying to sample from is a posterior distribution. Okay, so going back to this plot, I am not assuming a particular shape of the posterior distribution, other than the fact that you may have a typical set given by, I don't know, this thing. But this is just a cartoon in order to make a point here. And the point is that the idea is that you want to have some guidance. And then HMC is trying to do that. Okay. Okay, so we need, I mean, how do you do this? I mean, so in general, you may think, you may want information about the geometry of the typical set, right? So now you go try to think about a geometry of a function, or then you may think of a vector field. Let's say you have a vector field aligned with the typical set. So how can we obtain a vector field? So imagine that I have, let me try to draw this again. Imagine that I have a typical set here, and then you can obtain a vector field by the gradient. So you can use gradient of the function. But if you do that, you are actually getting gradients in this direction. I mean, the resulting vector field by taking just the gradient of the function will just, but you know, you may probably make the point. It is perpendicular to the typical set, while what you actually want is a vector field that is aligned with the typical set somehow. So you want something more like this vector field than the previous thing. And then here is where it comes, the idea of this orbiting. So the idea of this analogy with a physical system, and in particular, analogy with a satellite orbiting around the Earth. Sorry. Oops, I'm too fast. Okay. And this is the whole idea. And then you will have a satellite. This satellite would need some momentum, right? Satellites need momentum in order to maintain the equilibrium trajectory. And that is the whole thing. So now let me change notation. Let me call change notation now. Now my parameters are going to be given by a vector of Q. So the idea is to augment the parameter space going from Q to a pair of Q and associated momenta. So here, Pi is associated to the coordinate or the parameter Qi for every I. Okay, so you have a one-to-one association to that. And this means that then imagine that you have your target distribution. And then let me call it your target distribution is, let me call it pi of Q, will be augmented to a joint distribution Q of Q and P. And this will be called the canonical distribution. And this is like a joint distribution, right? So the way I put it. So this is equal to the distribution of P given Q times the distribution of Q. Okay. And in any case, what you recover this by marginalizing over P. Right. So this is like a joint PDF of our model in this particular case. So now we are focusing. Imagine I have a model, a Bayesian inference, and I want to estimate the posterior. And the way to implement this in this with this approach is that it will be enough to get samples from the joint. Will also be samples from the posterior, and this is this magical fact that you don't need the normalization here is just because the whole procedure of the Metropolis step. Okay, that we have discussed it before. We have discussed it in terms of this P tilde, right? This P tilde is nothing but the joint. And the whole thing is it works, and you in this approach. So in this approach, it is important message to get here is that so this approach doesn't need the normalization or the evidence. As opposed to other approaches in Bayesian inference. Okay. So we are just worried about getting as a target distribution it is actually the numerator of the Bayes theorem. Okay, so the canonical distribution will be written in the following form. So this P of Q and P, okay, pi of Q and P is written as the exponential of some function, which is nothing but the Hamiltonian. Okay. So this Hamiltonian of the system is a typical Hamiltonian, right? But then you will have Hamilton equations. Okay. So, but then nothing. The Hamiltonian will then be given by just minus log of the joint distribution. And then let me expand this joint distribution. So this will be minus log of the conditional of P given Q minus log of pi of Q, right? This is actually what you're interested in, no? This factor here is what you are interested in at the end of the day. I mean, all this augmentation of the system, of the parameter space, of associating to every parameter an associated moment, etc. All of this is just to get this at the end of the day. So this is written as the kinetic energy plus a potential energy and so this is just the target distribution is entering into this potential energy, let's say. Whereas this kinetic energy is actually unconstrained. Unconstrained. And it actually depends on the implementation. It depends on the particular implementation. And now, in order to get the desired vector field, which is aligned with the typical set, then you solve the Hamilton equations. So Hamilton equations, you may remember that. Derivative of Q with respect to T is just d HdP. This is obviously only affecting the kinetic energy. And the derivative of P with respect to T is minus dH dQ, which in general will affect both. And there you identify this as the gradient of the target distribution. think this is also called the forces, I mean, in the jargon of a lattice QCD. So what if the kinetic energy is like a sort of arbitrary? So what do you choose? So I tell you here about typical choices for the kinetic energy. So typically, this kinetic energy, which a priori actually depends on both variables, is chosen to be only depending on the momentum. And in general, it's chosen to be having the form of a kinetic energy with some, let's say, associated mass m. So m here is a positive definite mass matrix in a way. Okay. But since you know that K is the minus log of pi of P given Q, this implies that we're saying here, by choosing this kinetic energy, we are actually saying that the momenta follow a normal distribution of zero mean and covariance matrix M. So this is a covariance matrix of the multivariate Gaussian distribution. So this mass matrix is like the covariance matrix of the covariance distribution, of the distribution for P. Then what to choose about this covariance matrix? Then again, typically, let me just use another word, frequently, M is chosen to be either diagonal or even proportional to the identity. So you have only one parameter defining the whole distribution of your associated variables, this momentum. Okay. So let me just summarize the HMC algorithm. It is, as before, a two-step procedure where in each iteration you do two things. You sample P from your conditional, and this is giving you, let's say, at the very beginning, this may give you P0 at the beginning. Okay. And second, you perform a Metropolis step, or a Metropolis, let me call it update. And you do this by using Hamilton dynamics to propose a new state. Using Hamilton equations to propose a new state. So what you do is here, you solve the equations. Let me put it for a predefined time L, let's say. So I am trying to work out this transition here. Okay. So if I start with Q0 and P0, the current value of the canonical distribution is Q0, P0. Let me just call this pi 0. While the proposed state will have a canonical distribution given by pi star, and this new state will be accepted with probability given by the mean between 1 and pi star over pi 0, which is equal to the mean between 1 and e to the minus h star minus plus h0. Okay. Then it is just a matter of solve the Hamilton equations. So solving the Hamilton equations, this is just a deterministic step. I am solving the equation from for a given amount of time, L, and then I get a state after solving this equation, which then this is the stochastic step where I compare it with the previous step at the very beginning, and then I decide to accept it or not. So pictorially, I can just say, okay, imagine that I start from Q0 here, and then, or Q0, P0 in general. And then this transition, it is deterministic, because this is involving the solution of the Hamilton equations. And then I get a final value of this pair, which I compare. So I compare this with this stochastically, no? Stochastically. By following the Metropolis step. Okay. Now there are many ways of, but this is just a matter of having a numerical method to solve Hamilton equations. So you could think of the Euler method, and that you may also be familiarized with. So you probably have it in your studies, which is this. I'm just solving the Hamilton equations using this numerical procedure here. So I'm just shifting by epsilon. And this is t plus epsilon times. Now I am using the fact that the kinetic energy is just a number. I mean, in this case, yeah. So here in general, it is like a diagonal kinetic energy where every component has its own m. Let's say that's why you have an ion m. So and then you choose this. You choose epsilon, and then you choose L, in the trajectory, the length of the trajectory, and then you go for it. The problem is that this is not good enough, and I will show you later a result on that. And what typically is used nowadays is something called leapfrog method, which is a refinement on that, which works much better. And the refinement goes in the direction of having first half a step from the momenta minus epsilon over 2 dv dqi, then have a full step of the positions qit plus epsilon pi t plus epsilon 2 over mi, and then having a second shift on the moment. And I mean, this is a whole discussion on why this has good properties. I will show you just an example on that. Let me try to share screen. Let me go to my other screen, sorry. Share screen. Yeah. Let me see if it is. This is the paper. This is a very good paper of having a review on this. I will show you later the reference. But the Euler method. Imagine that you are trying to sample from this distribution. So do you see my screen, by the way?
Yes, we can see your screen.
Okay, so the Euler method, okay, depending on the step size, it's going to be better or worse, but in general, the Euler method is not going to, I mean, it could diverge actually. And this is the plot at the left panel. There is a modification of the Euler method, which is much better. But actually what people are doing now is actually leapfrog or refinements of leapfrog, where you actually have a much better properties. And even though you may have a very large step size, I mean, it more or less give you some good coverage. I mean, it is ergodic. I mean, it is the results. I mean, in general, you need to tune it, but it is ergodic, let's say. So yeah, so I was preparing a code for that, but I don't know if it is too much to start showing you a code. Let me go directly. This is a leapfrog method I was trying to write. Let me go directly to, now that I have a paper here and showing you, go directly to the algorithm. So this function, you can implement this function very easily, where you have a function of your target distribution and on the gradient of your target distribution, and it will depend on an epsilon because of numerical integration, right? Epsilon and L, and it will depend on the current state that you have. So this is a function that gives you, starting from Q0, it will give you Q star, or if it is accepted, and if it is not accepted, it will give you Q0. So it is going back to the same point if it is rejected. And then it is just, okay, sampling P from the normal distribution, so this part, and implementing the leapfrog, which is making a half a step for the momenta, and then going the whole trajectory, doing these alternating steps between P and epsilon, and finally making a half a step for the momenta again, as the leapfrog is the recipe is giving you. You can forget about this, which doesn't have an effect for us because the kinetic energy is symmetric with respect to P. But nothing. Once you solve the Hamilton equations and you get the proposed Q, storing Q and P here, you can compute the proposed potential energy, the proposed kinetic energy, and build your proposed Hamiltonian and you compare it with the Hamiltonian that you get from the beginning, from the current, right? So, which means you have a random number, and then if this random number is larger than the acceptance probability, then you reject the point, or otherwise you accept it. And this is more or less some results of a very small example where you have only one variable, only one parameter, two parameters. You have here two parameters. And this is a particular implementation that you can follow in this paper I can give you to have this. But that's pretty much it. I don't want to get delayed in some like numerical details, but I would like to know if the message is here, if it is passed, of what is the general purpose of HMC and why it is better than the other methods. Okay, so maybe I stop here, and then if there is any question, we can discuss.
I have a question about this method, in the sense that it seems that the mass and the length of the step are more or less arbitrary. So how would we choose them in practice?
Yeah, in practice, yeah, this is a good question. So let me go back to the leapfrog equation. Hopefully it is upstairs. Yeah, so in practice, people, they just use one parameter, not one mass for every component, but only one parameter. But in any case, note that if you change the mass, you can actually, in a way, not completely, but partially reabsorb this by a choice of epsilon. Right, so again, partially by increasing the mass or decreasing the mass will just mean that you may have the same answer if you play with the epsilon. Okay, so this paper I give you, it is like actually very, I mean, it is not that it is easy to read, but I mean, it is clear at least, so you may go for it if you're interested. It is like giving you recipes for, okay, typically what you choose of the parameters, etc., in order to get a good convergence, etc. The HMC depends quite heavily on the good choice of epsilon and L. And actually, there is a combination which is epsilon times L, which is particularly important. But I mean, this is just, yeah, this is another lengthy discussion that we may not have time to have now. But indeed, yeah, in particularly concerning the question of the mass, there is this partial reabsorption effect of epsilon that tells you that probably if you get a mass equal 1, as is typically done, then you're good to go. So here, in the example he was showing, let me ergodicity, illustrations, etc. Yeah, I wanted to, yes, yeah, this equation here, right, at the bottom of the page. This equation here. So kinetic energy is p²/2 essentially, and this means that he has used the mass equal 1, and it works actually. But I mean, there is a whole discussion about the tuning the parameters, etc., that it is interesting to follow in this paper. And this is, by the way, just maybe good to show the reference. So this is just this paper. The archive number is this one. Okay, so this is a paper. Actually, it's very funny because I mean this is a paper by this Radford Neal, which is very famous. But it is probably the paper which made famous the procedure in the machine learning community, and he imported it from the lattice QCD community. So in a way, it is interesting to see that the state of the art of Monte Carlo studies in machine learning, they come from physics. But yeah, any other question?
Also, the derivative of the like the potential and so on, is it usually done analytically?
No.
Assuming that the posterior is the likelihood times the prior, and that you know the derivatives of these things, or
no,
is it done numerically?
This is done typically in a realistic scenario. This is typically done numerically. So you have one of these tools for automatic differentiation I was talking you about, like TensorFlow or PyTorch or whatever. You need automatic differentiation for this. So in general, this potential energy is very complicated because it is your target distribution in a way. And computing the derivative with respect to a complicated function, it is only feasible nowadays if you use automatic differentiation. So you may need a tool that tells, okay, I have defined this function, and function of these parameters. This can have inside the neural networks or whatever you want. And with this tool, they just give an answer of the gradients of this function with respect to the parameters. Okay.
Okay, so it's done numerical.
Yes, in general, it is done numerical. Yeah, absolutely. Any other question? From you, Gonzalo, or any other person? You don't be shy. I mean. Okay, it seems not. So with this, we finish this course, these lectures, and then okay. Thanks a lot for joining, and I hope you have learned something. Okay.
Thank you very much for the course, Brian. It was very nice.
Thanks a lot.
Thank you very much, Brian.
See you soon.
See you next week.
See you.